Go ahead.
Yeah, thanks, Sam. Thanks everyone for coming. So I want to talk about this sort of categorical local Langlands conjecture. So this is some conjecture that came out of recent work of Farg and Scholze, where they basically showed that you could realize the local Langlands correspondence for p-adic reductive groups in terms of some geometric Langlands correspondence coming from this Farg-Fontaine curve. This is just some curve coming from p-adic Hodge theory. So that's all very, very technical, and it's very difficult to define exactly what I even mean when I say these words. But I just want to kind of give you some idea for what kind of questions this thing addresses and how one can kind of make progress on it, at least from my point of view. All right, so I'm going to try and do some motivation. So what's something number theorists care about? Well, we consider a Shimura datum. So G is going to be some connective reductive group over, let's just say, the rational numbers, and X is going to be some co-character satisfying, certain axioms. And whatever those axioms are, it should be the case that attached to this thing, a family is indexed by compact open subgroups in the finite adelic points of this reductive group G. So we get some family like this, and this thing should be defined over, let's just say, the rational numbers. Consider the base change, the algebraic closure, and the point is that this has two simultaneous actions on it. So one is given by the absolute Gauss logarithm 2, and the other one is given by a Hecke operators by the finite adelic points of this group. And so the point is we want to understand the geometry of these spaces better, and in particular look at their L-adic cohomology and decompose it with respect to these two actions. And the point is these generalize things like the modular curve, and we know that the L-adic cohomology of the modular curve sees the Galois representations attached to modular forms. So that's something we'd like to understand better. And so we'd like to gain more insight into the geometry of this. So one way you could do this, which is a perfectly good way of understanding this, is that you could view this as a complex analytic manifold. And then you have access to tools from differential geometry and things like that. You can use Hodge theory, and you can get some kind of picture for what the structure of this cohomology should look like. But that's maybe a little bit unsatisfactory, because when you do that, you forget a lot of information about the action of this Galois group here. And so what I want to do is do some kind of analog of that story in the p-adic way. So let me fix prime t. Let me write G for the base change of this group to QP. And so what I want to do is I want to consider spaces base change to the completed algebraic closure of the p-adic numbers. And then what I want to do is I want to regard this as kind of a adic space or a rigid analytic space or a p-adic manifold. Do this. So I get this space here. And the point is that passing to this category gives me some kind of additional flexibility. So in particular, one thing I can do is I can kind of consider the universal cover of this thing. So I'm going to write KP for the level away from P and KP for the level at P. I'm going to take the limit as the level at P approaches 1 of these spaces. And this I'm going to define to be space. So there's some issues with completing the structure sheet, but let's not worry about that. So this gives an example of what's called a perfectoid space. And it's not really so important what that exactly means for this talk. But the point is that this is sort of the minimal framework you need to do relative p-adic Hodge theory. So to do the p-adic analog of Hodge theory in families. So in particular, what that allows you to do is you can define a map going to say what this is in a second, that essentially records how the p-adic Hodge filtration looks like for the abelian varieties or elliptic curves that this Shimura variety is parameterized. So first, let me tell you what this is. So the point is you base change x to c, and you get kind of a co-character valued in 2 copies of GM, and then you choose some embedding, and you fix an isomorphism between c and q. And that defines for you a co-character mu as some kind of geometric co-character of this group. And then this thing over here, well, it's essentially just the flag variety attached to, so there's this inverse appearing to this co-character. And then again, we want to consider this as a p-adic manifold. And so, well, the p-adic Hodge filtration is something on the p-adic étoile cohomology of the abelian varieties or elliptic curves that this is parametrizing. And that has something to do with the p torsion of, say, the elliptic curve. And so if you open up Silverman or something like that, you'll see that there's a dichotomy in how the p torsion of an elliptic curve and characteristic p behaves based on whether the elliptic curve is ordinary or supersingular. And so it's reasonable to believe that the behavior of this map should be dictated by a similar kind of dichotomy. So formally, what I want to say here is that, I'll switch to move forward. So the behavior of this map is going to be dictated by some element in this set, e.g. mu, subset of what's called the couplet set G. So I'm not going to tell you exactly what this is, but let me give you a way of thinking about it. So let me explain the case of GLM. So roughly what these things are parametrizing is they're parametrizing sort of isocrystals with G structure on them. And so isocrystals are what you get if you look at p-divisible groups. You take their Dieudonné modules, and then you invert P. And the point is that that will model, that linear algebraic category will model the isogeny category of p-divisible groups, which will clearly appear in the Shimura variety picture. And so p-divisible groups admit a kind of slope classification. We can think of this elements of this set as just corresponding to some kind of polygons like this, where these are some rational numbers. Polygon ends at x equals n. And so what is this VG mu? So let me just explain the case of G equals GL2. So the situation of the modular curve. And mu is just going to be the co-character 1, 0. And so this co-character, we can regard it as just one of these polygons. So it has slope 1 and then slope 0. And then the point is there colored chalk? The point is that this set VG mu is going to be the set of all elements which lie underneath this polygon. And so in this case, you can see there's 2 of them. So one given by this 1, 0, and the other one given by this slope 1 half. And so the point is that this corresponds to the supersingular locus, and this orange one corresponds to the ordinary locus. And so what exactly do we mean by that? Well, the point is that these elements B and VG mu, they stratify this flag variety. And so this space breaks up into some pieces like this. And these 2 pieces that you get from this procedure for the modular curve are just going to be basically the rigid generic fibers of the usual ordinary and supersingular locus inside the modular curve. So this is some vast generalization of this. So again, we wanted to understand the geometry of these spaces. And so the point is that we can reduce the problem of understanding the geometry of the space to understanding the geometry of these individual pieces. And each of these individual pieces admit a kind of simpler description. So the point is that they break up into a product of 2 spaces. So one of these spaces I'll call Stuka GB mu infinity. I'm going to be a little bit sloppy here, but this is a product modulo some kind of group action with this thing, which I'll call a BKP. And so this is what's called an Igusa variety. So I might say something about these Igusa varieties, but in this ordinary case, for example, these will basically be relate to the Igusa varieties that you might have seen in like the book of Katz-Mazer, for example.
Sorry, can you read out what you just wrote? The whole line. Stuka J key mu, and then
this is one space, and this is another space. And I'm going to tell you what this JB is in a second.
I was just wondering if you could read all the symbols. So like JK, and then
Stuka G B mu JB times JB Ig KP B. Sorry. Don't worry about it.
Okay, and what's the subscript for the Stuka space?
Oh, it's infinity.
Okay, great, excellent.
Yeah. All right. I mean, the Igusa varieties are very interesting, but I don't really have anything to tell you about them today. So the point is, I'm going to be more or less interested in telling you how you can understand these spaces over here. So what is this? Well, it was noted, I guess by Farg and probably Scholze and Weinstein at roughly the same time, that this set G classifies G bundles, so on some curve X. So I'm not going to define this curve for you. It's complicated. It comes from chaotic Hodge theory. But I mean, roughly, this is some kind of avatar of QP. So if you look at the étale fundamental group of this curve, it's the same thing as the absolute Galois group of QP. Okay. And so the point is that this space parameterizes modifications between the bundle corresponding to this element B we're looking at, EB, the trivial G bundle, E0, with meromorphy bounded by mu. So this is occurring on this curve X. And so what kind of symmetries does this space have? So it's going to be related to this JB. So Kottwitz, I think, introduced this thing because he was interested in stabilizing the trace formula on Shimura varieties. And so related to that is this observation that if you take any element inside here, you can associate to it some reductive group JB. So that okay, I have to impose some assumptions, but this is going to be essentially an inner form of a Levy subgroup G. So you can see why this would be relevant to the trace formula. So let me just give you an example. So in this super singular case, this JB is just going to be units in a division algebra of invariant 1/2. And it makes perfect sense that that would act on this space because this is the super singular locus of the modular curve. And this is going to be related to the endomorphism algebra of a super singular elliptic curve. And so the point is that this space, the automorphisms of these G bundles are going to be described by the QP points of these J.
What's the weight of a unit in the division algebra?
What? I mean, this is
What's
just
the 1/2?
this just means quaternion division algebra.
What's the 1/2?
Well, it's like if you view it in terms of classes in the Brouwer group, right? I would map to the thing 1/2. Yeah. So okay. And then the automorphisms of this trivial G bundle are given by the QP points of the reductive group G. And so, but remember this modification here, this is really occurring at some point inside this curve. And so this curve is recorded somehow in the Stuka space. And so it also has an action by the Vey group QP. And similarly, this thing also has an action by this JB. And so attached to this, you can define some complex, which I'll denote R gamma C GB mu. And then it also carries an action of all of these groups. And so roughly, we're going to be interested in describing the cohomology of these complexes. That's what this is really all about. And so, for example, for this supersingular case, this is really the generic fiber of the moduli space parameterizing deformations of Lubin-Tate formal groups. So this was understood by David and Carriol, and they showed that it realizes the local Langlands correspondence for GL2. These complexes do that. And so in particular, also because we have this group action by JB, we want to kind of modify this a little bit. So we want to consider some kind of row isotypic part. So this is just going to be the complex where I take my original thing, I tensor it over the smooth Heck algebra with my representation row. And so this will now have a leftover action of G of TP and W of TP. So this is what I'm just going to call this star. And so let me give you some idea for what star looks like.
Do you remember what row was?
Oh, sorry. I don't think I told you. Rho is just going to be a smooth ERF of JB. Yeah, sorry, I forgot to mention that. So what does star look like? Well, the point is it should be dictated by the local Langlands correspondence. So what is that? Well, if we consider the set of smooth ERFs of G, and then maybe also a smooth ERFs of JB, the point is that because these are inner forms, the local Langlands correspondence is going to take values in the same set. What is that set? So it's some conjugacy classes of maps of this form. And then it goes this way, right? And so also I should say I'm always kind of secretly fixing an isomorphism between L, R, and C. We're doing both of these with discrete topology. And so this thing over here is the reductive group with group datum dual to G. And this vague group action is kind of remembering the fact that that reductive group was initially defined over G. And so we expect some kind of map like this that compares Galois representations and these smooth representations. And anytime I talk about this thing, I'm always going to assume that if I take some phi in here, I can consider the fibers of this map. These are some sets which are called L packets. And in general, we expect that there should always be some kind of relationship between this because this is an inner form. And so I'm always going to assume that it satisfies what are called the endoscopic character identities. So roughly speaking, there's some way of comparing these two representations in the sense that certain orbital integrals defined by the members of these packets match up. All right. Okay, actually, yeah. So now let me try and explain to you how this complex behaves in various cases. So these are all conjectures, but I mean, so the first case I'm going to be interested in is when phi is a quote unquote supercuspidal parameter. So what does this mean? This means that the SL2 factor acts trivially, so there's no monodromy, and that this parameter does not factor through the L group of any like subgroup of G. And the point is that this is precisely the case in which these L packets are just going to consist solely of supercuspidal representation, in which we expect that to be true. And so, roughly, okay, I want to describe this complex star. And so what is the vague group action going to look like? Well, recall that this co-character mu is going to correspond to some highest weight representation of this Langlands spool group. So we get some kind of map like this. And roughly, we expect the vague group action on this complex to always be given by this co-character composed of phi. So this will break up into a direct sum of irreducible representations. And then, well, what do we expect? So first off, let me maybe say some broad things about this. So the cohomology of this complex is always going to be concentrated in degrees 0 through 2D, where D is basically the dimension of this flag variety that I originally started with. So this is the sum of all the positive roots. And so in this case, the way we expect the cohomology to look is that it breaks up as a direct sum of this form, these irreducible summands. And then the G of QP action on this is going to be given by some representations pi I, where pi I are in the L packet of this parameter over G. And then the key point is that this is going to be concentrated in middle dimension, in middle degree in this case. There's also some tape twists here, but I'm just going to pretend those don't exist for this talk. So yeah. So again, you might not be familiar with these spaces. They might seem very strange to you, but roughly, I mean, one way you can kind of think of this is that these are some spaces occurring from a chaotic uniformization of this Chamorro variety. Just like symmetric spaces occur from the uniformization of the Chamorro variety as a complex analytic space. And so you can roughly think of this as some kind of analog of GK cohomology. And so, for example, as I'm going to show you in a second, in the cases in which this SL2 factor acts trivially so that there's no monodromy, then we're going to see that the cohomology is concentrated in middle degree. And similarly, you see that, for cohomological tempered representations, that the GK cohomology is also concentrated in middle degree. And in fact, that's really no accident, because the point is that classically, if you wanted to prove such a theorem like this, you would use uniformization to relate this to a problem, the global Chamorro variety. And that would involve globalizing the representation rho that you started with. And what rho is going to basically have an impact on what the Archimedean component of that representation will look like. So if rho is supercuspidal, like in this case, then you can allow it to be regular, cohomological, all these good things. But if it's non-tempered, then that will also cause the the Archimedean component to be tempered. So yeah, maybe that gives you some idea. So case B, I'm going to tell you about is when phi has no monodromy. But it's not discrete. So that means it factors through some Levy subgroup. Induced from some parameter factoring through a Levy subgroup of this. And so, okay, I forgot this. So in this case, there's some rigid constraint imposed on the element B you need to choose. So in this case, B has to be what's called basic. And so that corresponds to these sort of minimal elements on the partial ordering on polygons. So like this isoclinic guy. And the point is that when B is basic, that is equivalent to JB not just being an inner form of a Levy subgroup, but being an inner form of G, like this division algebra. And so for this to make sense, you kind of need that B has to be basic, because otherwise rho lying in the L packet, so rho lying in this L packet, would immediately imply that the parameter factors through a Levy subgroup. So that would contradict the fact that it's supercuspidal. But in this case, sort of what happens is that B roughly has to correspond to some highest weight of a representation in sort of rep Ln. So I'm going to denote this highest weight by UV. Rather some sort of bio orbit. Well, okay, it said highest weight, so it's fine. And so the point is that, for example, if it factors to the maximal torus, in this case, in this GL2 case, the only contribution should come from this kind of ordinary element. And so I can then compose my parameter phi m. So my parameter phi m with this thing. And so it again breaks up as a direct sum of irreducible representations like this. And then my star, in this case, is going to be isomorphic to, again, these phi I appearing here, together with sort of the normalized parabolic inductions of some pi I m, which will be members of the L packet over the supercuspidal parameter of m. And then there's something relating to this co-character nu So there's some kind of weight space that gets tensored by this. And so this is not quite concentrated in middle degree, but middle degree offset by some quantity coming from the slope polygon. This is the slope polygon of this element U B. And so roughly you can think of this case as being the parabolic induction of this case. So case A is was basically first conjectured by Kottwitz and then later refined by some other people. In case B, well, this is something maybe a little bit more new. I don't know, I mean, certainly some people are aware of this, but yeah, I mean, so sorry, are there any questions on these two examples here?
So when Kottwitz was doing this, he wasn't using maybe Uber language. I mean, he's comparing uniform trace formula.
Mm-hmm.
Usually when he does anything like that, there's no restriction to the chronological unless you want to interpret it because it's comparing. So when you say he conjectured, what exactly did he conjecture?
Well, I mean, he conjectured essentially this, but in the Verdi group. I mean, well, Kottwitz, I mean, so I've been using this newer language to think about these things, but Kottwitz, I mean, roughly you could think of this as some sort of moduli space of p-divisible groups if you work integrally or something like this and at finite level. And then these Igusa varieties also have a similar description at finite level. And so Kottwitz was interested if you take some test function, right, and you integrate it against, say, the cohomology of these spaces, what does that look like roughly? So that's somehow how he developed this whole language. And he basically guessed from doing computations, I guess, that the contribution of this, at least in the Verdi group, and in this case, should break up as something like this. I mean, I'm not an expert in this, but I think that's roughly how this goes. Are there any other questions? All right, okay. Let me just say, okay, maybe I should skip case C. Is there an eraser? So case C is when phi has monodromy. And this is really kind of very mysterious. So I'm just going to say case C is when phi has monodromy. And in this case, I'm just going to put a big question mark here. So, I mean, roughly, okay, let me tell you one thing. So again, we expect the Weil group action to be given by sort of this co-character mu composed with phi. But again, that's still true here because this is a weight space of this mu. Oh, thanks. And so, well, this doesn't really make sense because phi has this SL2 factor acting. And so what you really need to do is you need to consider the semi-simplification. So the semi-simplification is just you take this parameter phi and you precompose it with the map that sends G in W of T to G, comma, this determinant one matrix. And so the point is that you're killing the unipotent part, and so you're killing the monodromy. And then roughly, so the cohomology is not going to be concentrated in a single degree, so it's going to be concentrated in multiple degrees. And roughly speaking, you can recover the action of this SL2 from the fact that it's concentrated in multiple degrees and a Lefschetz operator coming from this flag variety over here. And so if you're curious about this, I mean, a great example to do of this stuff is just the case of the trivial representation. And so this is work of Schneider and Schuler. There it's just going to be the cohomology of the Drinfeld upper half plane. And then sort of Dot also has a great paper where he studies this in more generality and he makes this heuristic with the Lefschetz operator true. And then in general, there's some, well, work of Ito for GU12 and Ito and Meta for GSP4. And roughly speaking, I mean, one thing they note is that on the one hand, you see this L packet here. You also see some kind of A packet where this is sort of the A parameter that you attach to phi. And so, for example, this thing is going to see some non-tempered representations. And so by the same analogy, which you take cohomology, you expect that things are going to get really weird. So this is really, I have no idea what's happening here in general, But somehow if you could understand these two cases well enough, maybe you could understand that. So this is really what I mean. Okay, so what's the point? So I haven't mentioned anything. I think I've written down a single category. We don't plan on doing. But what does this have to do with the abstract of my talk? So the point is we don't know that this thing exists in general. But very recently, we know that we always have a map from pi g to the set of semi-simple parameters. Again, that's like the semi-simplification. These are just maps from the and so the point is that we should believe, or that we expect this to be the quote unquote, sorry, so this is the Varieties local Langlands correspondence. And so this was defined using some kind of geometric local Langlands. And we showed it has various good properties. And in general, we believe that this should be the true local Langlands correspondence. So if we have some map like this, then if we consider this map given by a semi-simplification, then we expect that this diagram should always commute for any good candidate of the local Langlands correspondence. And the point of the categorical conjecture in some sense is that maybe this parameter doesn't exist, but this one always does. And this one basically, if the parameter behaves like I'm saying here, then the cohomology will look like this via some methods in geometric Langlands. And so this leads to kind of a paradigm shift in how you prove theorems about this cohomology. So roughly, when I say make progress, there are two steps, which is show that this diagram commutes. So show compatibility. And then B, use A to verify these expectations using some kind of geometric Langlands techniques. So let me start with telling you a little bit about A. So again, I don't really know how I'm supposed to talk about this stuff. So I'm sorry if
Can you just say again what all the arrows are, the diagram?
what?
Like,
Oh yeah, sure. So this, I'm just saying that, like, say you have some candidate for the local Langlands correspondence, like the Harris-Taylor correspondence. Then this map is the semi-simplification map. So just the map where you take your G, your parameter, and you pre-compose it with this map from WTP times SL2. Then you expect that if this is a good candidate, that this diagram should commute where this is going to be the Varieties local Langlands correspondence.
Okay.
So that takes values in semi-simple L parameters. So
neither of those maps are this map. Like, what's the relationship between?
no, this. Well, the point is they should be.
Okay.
They should be. I'm going to tell you about that. But I mean, when I say the local Langlands, I mean the precise sense. I mean, the way Khalifa has formulated it. It's refined local Langlands correspondence, where you have some description of the L packets in terms of the centralizer, and then endoscopic character identities and this kind of business. Okay, so let me just tell you what's
Can I
true.
ask you a much more basic question? Suppose that you succeed with this, could you be telling me what the supercategorical representations are? Explicitly something?
What the super? No, not.
You're just going to say it's people do something else.
Well, this talk isn't going to be about that, but I mean, I'm not
I'm just
really.
curious,
I'm not
what kind
really
of
going to be
information?
saying anything about the structure of this local Langlands correspondence. I mean, lots of smart people have much better ways than me of understanding this. My point is, if you know it already, to show it agrees with this Varieties local Langlands correspondence, and then use that to deduce these conjectures I've been making about the cohomology of these local Shimura varieties, which then provide more insight into the global Shimura variety itself. That's sort of the point. But yeah, I mean, Varieties doesn't really tell you anything about the structure of this. I mean, basic properties, but nothing too refined. All right, so let me just tell you what's true in terms of knowing that this diagram commutes. So for GLN and its inner forms, well, And this is the Harris-Taylor correspondence. And so this conjecture A, I mean, this was essentially verified by Harris-Taylor. And this thing about it being concentrated in middle degrees, I guess you did dot, I'm not really sure. And then, so the point is that roughly these are some spaces of modifications. And so they compute Hecke operators on this moduli stack of G bundles. And so the excursion algebra, which defines this parameter, is built from Hecke operators. So essentially using the work of Harris-Taylor, you can compute the excursion operators in this case, and so you can deduce compatibility. So this is already in the paper of Farg and Scholze. And then, so Hansen, Khalifa, and Weinstein basically also deduced it for all the inner forms. And so then there's the case of GSP4 and its unique non-split inner form GU2D. This is the quaternion division algebra. So here the local Langlands corresponds together with the endoscopic character identities of Gahn, Takeda, Cantono, and Nchan. And so here compatibility is a theorem of myself. And then the other last case in which some progress has been made is sort of odd unramified unitary groups. So in this case, so Bertoloni-Melli, a student of some,
also getting it from global consideration.
yeah, they get it from theta correspondences. It's built from Harris-Taylor and theta correspondences. So Alexander Bertoloni-Melli, a student of Sagwu Shin, together with Kye-Hugh Nguyen, a student of Pascal Boyer and Laurent Farg, basically verified this kind of conjecture in the Burgundy group. And so using kind of arguments in the style of Popwitz originally. And so if you combine that with some of the ideas I developed for GSP4, it gives you compatibility. And so then we can actually deduce this more refined claim on the structure of the cohomology.
Why the odd group?
Oh, why the odd group? So actually, it's probably not necessary. But the real reason is that so there's this funny thing that if you know the local Langlands corresponds for UN OAs, and then you want to work with EL and PL type Shimura varieties, so you want to go to GUN. And so you want to deduce the local Langlands corresponds for GUN. But if n is odd, then you know that UN and its center generate GUN. But that fails if n is even. So you have to solve this liftability question. But nowadays, you could probably just work directly with the even unitary Shimura variety. But yeah, that's a good question. Yeah. All right, so okay. So let me give you some insight into how we prove these kinds of things. So sketch of A. And so, well, GLM is in some sense too easy. Well, I don't know, but I'm going to do this case, GSP4. So okay, what's the datum I'm going to take here for G is GSP4? U is going to be this kind of, so again, for simplicity, I'm just going to work over QP, but what I do works for arbitrary, more general extensions. I'm going to take my co-character to be this 1, 1, 0, 0 character. So this Siegel co-character. Then B is going to be this kind of basic element. And so it's going to define an inner form. That inner form is GU2D. So I want to show compatibility. So roughly using Hansen, Khalifa, and Weinstein, doing it for the group and doing it for its inner form are in some sense equivalent if you know the endoscopic character identities already. I'm just going to explain this for the inner form. And so the first thing you do is you realize that you can reduce the case that rho is supercustable. And the reason for this is that for any Levy subgroup of this group or its inner form, you already know compatibility. And both Farg-Scholze and this Gahn-Takeda Cantono local Langlands correspondence are also compatible with parabolic induction. And so from then, it's essentially formal that you can assume that rho is supercuspal. So you want to show that this diagram commutes for this rho. And so what do you want to assume? You want to assume that if phi is the L parameter attached to rho, that this is supercuspal. And so this is different from insisting that rho is supercuspal. The reason is that phi being supercuspal means that not only rho, but all the other members of the L packet are also supercuspal representations. And for GSP4, that can fail. And so what's the issue here? So for example, let's suppose phi has the following form. Oh, I should also say that for this co-character mu, this representation R mu that I was talking about here, of the Langlands dual group of GSP4 is JD spin 5 / GSP4. This R mu is just the standard embedding of GSP4 into GL4. And the fact that a minuscule co-character gives rise to this nice embedding is basically the main thing that doesn't generalize these arguments. So let's suppose that standard composed with phi breaks up as a two-dimensional representation of WQP, so no monodromy. Direct sum with a character listed by the unique two-dimensional representation of SL2. So we have monodromy. So this is not a supercuspal parameter. So this is the quote-unquote sort of Howie-Piatetsky hero type case, because in the global situation,
Roger Howe.
yeah, Roger. Oh, sorry, Howie. Yeah, my bad. That's embarrassing. Yeah, How? So they study basically the global representations with these L parameters as part of finding counterexamples to the Moonaghan conjecture. And so what happens to the packets in this case? Well, you get a mix of a supercuspal representation and a discrete series non-supercuspal. And the same thing happens for JP. So the other case in which this can happen is this Saito-Kurokawa type case. And so, yeah, the proof is more or less the same in that case. So I'm just going to explain it for this. And so what's the point? Well, the point is we know compatibility already for these non-supercuspal guys, and we'd like to deduce compatibility for these supercuspal ones. And so I wish I could provide more detail on this, but it essentially reduces to the following fact, which is implicit in this paper of Hansen, Belitha, and Weinstein, which is that if LLC satisfies the endoscopic character identities, then it follows actually, then Farge-Schulze is constant on L packets. So I can give you some idea how to prove this. So roughly, what they show is that you assume the endoscopic character identities, then if you look at these kind of complexes that we're trying to study at these local Schmor varieties in the Berkeley group, then by some Lefschetz trace formula arguments, that will see the Hari-Chandra characters of the representations in the L packet. But on the other hand, this is really some Hecke operator applied to some representation given by this rho. And then the Hecke operators commute with the excursion algebra. And so the point is that everything that occurs in that complex, all the members of this L packet will have Farge-Schulze parameter equal to the rho that you originally started with. And so using that, you can deduce this claim, modulo some details. And so what's the point of this for us? The point is that, okay, for this guy, for this non-supercuspal guy, we know that the Farge-Schulze parameter agrees with this supercuspal guy. And then this, Okay, so this is equal to the semi-simplification of the usual parameter, but then by definition, that's the same as the semi-simplification of the supercuspidal parameter. So we conclude the equality that we want. So this allows us to deduce it in these cases. And so now we're interested in this supercuspidal case. And actually, this is very important that we're in this case. I'm going to apply the trace formula in a second. And so this is actually very important, this case, to make all of that work. So let me give you some idea for how to prove this. So the key here is the following fact, which is proven. So this is a general fact. It's not just for GSP4. So it's due to myself, and while I was writing up the argument, Koshikawa, a student of Kato, gave a proof of a very similar statement through a slightly different method. In any case, the upshot is still the same. So if phi 0 is an irreducible WQP representation and occurs as a subquotient of R mu composed with, occurs as a subquotient of this complex, then phi 0 is a sum end of R mu composed with phi rho. So in particular, anytime you compute anything about the Wegener action of this complex through global methods or what have you, you've said something about the Farr-Schulze parameter of this representation composed with this cocharacter. And so you can see that Harris-Taylor will basically immediately imply the statement we want from this, this GLM case. So this is actually quite tricky to prove, so I'm not going to do it. But the point is, this reduces us to the following. So we consider the direct sum over all representations in the supercuspidal L packet, and we look at their isotypic parts. And then we're reduced to showing that this has a subquotient with WQP action given by standard composed with the parameter we're interested in. And so why is this? Well, first of all, the Farr-Schulze parameter of all of these representations are going to be the same using this fact of Hansen, Kalifa, and Weinstein. And so it suffices to exhibit a subquotient of any one of these. And then this fact, this one here, will imply that standard composed with phi is the same thing as standard composed with phi rho Farr-Schulze for any row in this L packet. And then what's the point? Well, the GSP4 value parameter is determined by its composition with this embedding and its similitude character. But the similitude character is just the central character of the representation, and both Farr-Schulze and Gantantino are compatible with central characters. So this is enough to conclude what we want. So we're reduced to describing this complex. So now let me briefly explain how to do this. So first, are there any questions on why? Sorry, this is all very technical.
Yes, and sorry to repeat the question, but could you read the bottom line of the top word?
Maybe I should just, this complex, this has a subquotient with.
No, I meant up the top
Top
word.
word. Bottom line of the top word.
The row is a sub.
You didn't erase everything.
If phi 0 is an irreducible WQP representation and occurs as a subquotient of this complex, then phi 0 is a sum end of
what?
Phi rho Farr-Schulze, the Farr-Schulze parameter of this, composed with the representation of the Langlands dual group defined by mu. So in this case, the fact that we know that standard composed with phi occurs as a subquotient of this implies that standard composed with phi rho Farr-Schulze has to equal this. So Sorry, does that make sense?
I still can't read the symbols.
Yeah, you didn't
on the
erase
line
everything.
software. You just said it's
I
parameter.
think it's new subview or B subview or something, but then there's like some
There's some
It's like
unerased
R,
stuff.
unerased stuff.
left parentheses, subscript, superscript H,
I'm
Yeah,
sorry,
there's some-
circle.
I'm very confused.
The third line, I just can't read what's written there.
That's Lois. Yeah, sorry.
So what is written? What are the letters?
It's Pyro Farcholza. A composed with the co-character defined, the representation, the highest weight representation defined by this.
The character is R subscript mu.
Yeah, I write this as R subscript mu.
Okay,
This is in
R subscript mu is what I was looking for. Thanks.
Yeah. And in this case, it's just the standard. Okay.
Here you're still in a situation where JB is GU2.
Yeah. So sorry. In this, this fact is always true.
Okay.
So it's always true, even if it's not minuscule.
Okay.
But yeah, I'm using it in this case, right? Yeah. Okay. Cool. All right, what am I doing? So yeah, we want to prove this, and so the idea is that we use uniformization. And so the point is for these basic elements, this uniformization, this Igusa variety essentially becomes just a profinite set. So it becomes this profinite set here. I'll tell you. So KP is the level away from P. G prime is an inner form. So again, I'm just going to work over Q, inner form of GSP4 over Q non-split at P because it has to have an action of JB and also infinity. And so it's compact modulo center at infinity. And so in particular, that means we don't have to worry about any growth conditions. And so this is going to be some space of quote unquote algebraic automorphic forms with fixed and infinitesimal character given by this XC. And then the point is this defines some open strata by uniformization inside the homology of, well, I guess it's just the Siegel threefold in this case. And in fact, this map becomes an isomorphism with a slight modification. So we can project to the Bernstein component, this is SC, where G of QP acts via a supercuspidal representation. And then if you do that, this map becomes an isomorphism. So in the GLN setting, this is what's known as Boyer's trick. Roughly speaking, the non-basic elements of the flag variety are going to be parabolically induced as spaces. And so all the non-basic strata die if you do this projection. Okay, and this is pretty good because now we can pass between this local Chamorro variety and this global Chamorro variety very easily, and then apply the trace formula to the right-hand side. So what do? Well, we can take our rho and we can globalize it. So maybe I'll write this here. We can take our rho and then we can globalize it to a cusp form occurring in this. And so one important thing to note about this is that because rho is supercuspidal, you have a lot of freedom in how you choose this globalization. So you can make it regular cohomological at infinity. You can make it Steinberg at as many places as you want. And so that means that if you apply the trace formula, all the contributions of the Eisenstein series will die, and you get a nice simple trace formula, and even somebody like me can use it. Yeah, sorry. This is the only way I know to work with this stuff.
You're not the first to do this.
Yeah. So in particular, what we can establish is, so okay, let me first state what I want. So the Satake parameters of this thing will define a maximal ideal in the unramified in the spherical Hecke algebra away from some finite set of finite places. And so we can localize this map at that maximal ideal. And then what we can prove is we can prove some kind of strong multiplicity 1 result. And so what that does In particular, what that says is that, okay, so you need to do some further modification where you enforce some Steinberg assumption at finite many places. But then what it'll say is that all the automorphic representations of G prime occurring in the left-hand side will have Tantono parameter at P given by phi. And all the automorphic representations on the right side will have Takeda parameter at P given by a phi. And so that's great because that means that the left-hand side up to multiplicity will just break up in terms of this sum over here. So these are the members of that L packet. And then for the right-hand side, you can use work of, okay, maybe in this case, Pret and Shin isn't really necessary, but work of Pret and Shin, where they compute the traces of Frobenius on the right-hand side using the Langlands-Rappaport formula. So it's proven by Kissen, Shin, and Zhu very recently, together with the local global compatibility result of Klaus Sorensen to show WQP action given by standard composed with phi. So that roughly finishes the proof. Okay. So I basically explained to you how to show that partials increase with this. So I don't have that much time, but there's one more thing I wanted to say, which is roughly how you can use this compatibility to deduce these results on cohomology that I conjectured. So is it okay if I go a little over? I don't know. Or first of all, does anyone have any questions? Okay.
I mean, you said at some point that you had motivation for. You mentioned some extrinsic motivation at some point.
Well, the extrinsic motivation is really to exactly describe the cohomology of these complexes. So you see, I gave some very indirect description of this argument to deduce compatibility. But the point is once you know compatibility, then you have access to all these tools from Farr-Schulze, which you can combine with what you know about the local Langlands correspondence to basically completely describe these complexes in certain cases. So this is the part I haven't told you about yet. I mean, very, very roughly speaking. So if you take one of these phi supercuspidals, then geometric Langlands gives you a lot of tools for constructing Eigen Sheets. So this is going to be a sheaf on bun G, the moduli stack of G bundles of this curve. And so the fact that this is an eigensheaf with respect to a supercuspidal parameter basically means it's going to be supported on certain elements defined by these isoclinic things. So these basic elements. And each of these is isomorphic to a classifying stack of these inner forms. And so now the point is that using lots of tools from Farr-Schulze and what we know about the local Langlands correspondence, we can deduce from compatibility that the stalks of this eigensheaf at these basic strata are given via the direct sum over the L packet with respect to the supercuspidal parameter phi. So the way this thing works out is that giving a sheaf on this thing is the same as giving a complex of smoothly reducible representations. And so this thing is an eigensheaf. So if you take some Hecke operator defined by some cocharacter mu, that means that you get the eigensheaf together with R mu composed with phi. So what happens if you restrict this? Well, so what's going to happen is that this is really given by a tensoring by the cohomology of some space of modifications of type mu. But that was precisely the definition of these Stuka spaces. And so this thing over here will become, I'm just saying it in the case that mu is minuscule, will become the direct sum over these complexes of these rho. And then there's some perverse shift via this Hecke operator. And then you get what you get at the neutral component. So it's the direct sum for the members of the L packet. So if you move this shift over here, you get precisely this expectation that I was saying before, that the cohomology that's complex should be concentrated in middle degree. So D is the dimension of the space. And it should be valued, sorry, there's also pi R mu plus pi, and it should be given by representations in the L packet paired with the irreducible sum ends of this thing over here. And so actually, once you have these Eigen Sheets, then you can generate more. You can actually parabolically induce these things, and then you can describe the cohomology, how these certain irreducible parabolic inductions contribute to cohomology. That's something I've been working on recently. Yeah, roughly this is the point. So hopefully that was somewhat interesting.
Cool. Let's thank Linus.
What about groups of local Langlands which are purely local?
So first off, like one thing is you can see that these Eigen Sheets, they encode the different members of the L packet for the different inner forms for supercuspidal things. And so one thing you can wonder about is for GLN, can you construct this Eigen Sheet purely locally and show it has these properties? And so in the classical geometric Langlands program, people know how to do this. And so here you would do something similar, but you have to be a lot more explicit. And so I think, yeah, just I don't I don't think even in the classical geometric Langlands program people know it. I mean, in certain cases they do, but yeah. So there's a work of Johannes Anschutz and Arthur César Labras, where recently they study some kind of Fourier transform in this kind of setup, and they see that it sees sort of the formal degree of representations. And so that kind of hints that maybe something like this could work along these lines. But in general, I'm a little bit skeptical. So yeah. But yeah, I think what this is really good for is like shedding more light on the cohomology of these local and global Shimura varieties. Like for example, there was recently a paper of Koshikawa, who I mentioned, where he vastly simplified these torsion vanishing results of Cariani and Schulze. And one of the key inputs was knowing compatibility of Fard-Schulze with Harris Taylor. So that's like one really nice application of these things.
How about author parameters? Is that something about the non-tempered stuff? You get any insight into?
Well, so again, this is the most confusing situation. So I mentioned this before. So this is when the parameter is monodromy, and then you see sort of these members of the A packet in these local Shimura varieties. And so, well, one key thing that's really important here, that seems to be important in all the perspectives for understanding this, is if you look at the L packet and the A packet, it was observed by Hiraga that these things are interchanged at the contra gradients by something called the Zelevinsky integration. So it's defined by Schneider and Stuhler. And this admits some incarnation in this geometric Langlands framework. And so, for example, I have a very short preprint where I show how you can reprove some old results on how the Zelevinsky evolution acts. In this case, it's using those kinds of ideas. But in general, yeah, this will be the last case that people understand. I mean, I don't think people even understand how the GK cohomology looks in general in these cases, as far as I know. Maybe they do. Yeah, in general, it's you should see Arthur parameters, but yeah, it's very confusing. All right, sorry. Any other questions?
Any questions on Zoom? You can feel free to unmute yourself.
You said it was crucial in your argument that the representation that into the standard.
Yeah.
Where do you use that?
So it's in this implication right here. Because the point is that knowing the parameter composed with the standard representation and its similitude character determine the original parameter. But for example, say you tried to run this argument for like GSP6, then the issue is that the minuscule co-character you would get would correspond to the spin representation. And so all you could prove for these methods is that the parameters composed with spin agree. And then, well, then you can't deduce this implication in general. And so, for example, this is true for unitary groups, like the base change parameter determines the original parameter. It's true for odd or even special orthogonal groups. I forget which one. And so these are probably the cases you could prove by these methods. And then for these other groups, well, there's some new idea that's needed.
Let's do the composition check. Does it still give you some information about the?
Yeah, I've actually wondered about that. I don't know. So one thing I actually wondered is for certain parameters, you could actually say that the spin representation composed with the parameter actually determines the original parameter. And then you could get some information about the L packets over that parameter. But this is some kind of, I mean, this is really just a question of representation theory. It's just not one that I know how to do. So, yeah. But yeah, it would be interesting to know whether you could do that. Any other questions?
Here or on Zoom? Well, if not, let's thank Linus one more time.